The universe seems to be expanding faster than all expectations. Fresh evidence suggests that the universe is expanding faster today than it did in its infancy, a difference that has set off a search to understand what cosmic forces could be at play. If confirmed, the changing rate, which is 9% faster than had been projected, would force us to reconsider a fundamental aspect of the cosmos. The result, announced in a new report publishing in the Astrophysical Journal, marks the latest in a long-running controversy over the Hubble constant, a key measure of the universe's age and expansion rate. In recent years, numerous studies have shown that measurements of the Hubble constant from the cosmic microwave background, the faint afterglow of the infant universe, are at odds with estimates from far younger stars, such as those in our Milky Way, even after taking into account other mysterious cosmic forces such as dark energy, which is accelerating the universe's expansion. The universe is outpacing all our expectations in its expansion, and that is very puzzling, says lead study author Adam Rees, an astronomer at Johns Hopkins University who co-won the 2011 Nobel Prize in Physics for helping discover dark energy. Some have argued that the discrepancy is a product of incomplete data or some unseen errors systematically pressing their thumbs on the scales. But based on fresh measurements of our cosmic neighborhood from the Hubble Space Telescope, Rees and his colleagues say that the mismatch is not only real, it's wider than ever. In the new study, Rees's team measures the Hubble constant to a value of 74.03 km per second per megaparsec, give or take 1.42. That's at odds with the best estimates from Planck, a European Space Agency telescope that made the best measurements to date of the cosmic microwave background. Planck's data pegs the Hubble constant at about 67.4 km per second per megaparsec, give or take 0.5. In statistical parlance, the difference between these two results stands at about 4.4 sigma, or 1 in -100,000 odds that the discrepancy is merely a fluke. To use an analogy, let's look at a 2-year-old and see how tall they are, and then try to figure out how tall they are going to be when they grow up. Then we could actually wait until they grow up and measure them, Rees says. If they far exceed that extrapolation, we'd have a real mystery on our hands. Something isn't right in our understanding of how this person grew. Clocking the universe, calculating the Hubble constant, and thus the expansion rate of the universe, based on the movements of stars requires two kinds of data: how far away a given star is, and how quickly it's receding from us. To measure a star's relative velocity, astronomers look for shifts in the star's emitted light. To measure distance, astronomers use a variety of tools, from straightforward geometry to careful observations of stars called Cepheid variables. These stars brighten and dim regularly, and the rate of these pulses is closely related to the star's overall brightness. The brighter the star, the more slowly it pulsates. Astronomers can use this relationship as a ruler. By measuring a Cepheid's pulse rate, astronomers can work out how luminous the star is, and by comparing that absolute brightness with the one we see, we can infer how far away the star is from us. Cepheids also can be combined with observations of certain kinds of stellar explosions to measure distances deeper and deeper into the cosmos. Astronomers have worked for years to assemble this cosmic distance ladder, and they're constantly trying to calibrate it ever more finely. For this study, Rees's team used the Hubble Space Telescope to peer at 70 Cepheids in the Large Magellanic Cloud, one of our Milky Way's irregularly shaped satellite galaxies. These new data let them more precisely estimate the distances between us and objects in the Large Magellanic Cloud, which in turn let them infer the Hubble constant with greater precision. Subscribe to our YouTube channel for more, and don't forget to like this video.